Welcome to Hart und Trocken. My name is Dirk Schiebon, and in this video I want to talk to you about the chain rule for differentiating composed functions. Suppose we have a function f and a function g. We then define the function capital F as the composite function g after f. G after f of x is defined as g of f of x. Intuitively, we first throw x into f, and then we throw f of x into g. Alternatively, we can think of x taken to some y by f, which in turn is taken to some number z by g. Intuitively, composing functions is a chaining process in which the output of the function f feeds the input of function g. Now we assume that both f and g are differentiable and that we know the respective derivatives f prime and g prime. What we don't know, however, is the derivative of the composite function capital F. This is where the chain rule enters the picture. The chain rule is a differentiation rule which helps to find the derivative of capital F based on the derivatives of f and g. The chain rule has the following form. Capital F prime of x equals g prime of f of x times f prime of x. Let us try to make this rule transparent by looking at a graphical illustration. We consider these two functions f and g. Then the composite function capital F equals g after f looks like this. We can verify that this is the right function by tracing back the chaining of f and g. We start with some point a on the x-axis. We then let the function f throw this value a onto the y-axis to get the function value f of a. We now want to throw that function value f of a into the function g according to the chaining process. For this purpose, we mirror the value f of a at the first bisecting line in order to project it onto the x-axis. Following the chaining process, we next let the function g throw the value f of a onto the y-axis, thus obtaining the value g of f of a. Now this value is the value of the composite function g after f for the value a. So if we want to draw a graph for this function, we have to draw that height over the point a, and that gives this point. Now remember, we wanted to verify that the yellow curve is the correct graph for the composite function g after f. So the fact that this point, which is built by the coordinate a and the function value of the composite function at a, lies on the yellow curve is a first verification. Of course, we have a better feeling if we verify this for all values of a. That means if we move a along the x-axis. Well, we can do one step in this direction by animating the position of a. So we were able to verify that this yellow point nicely follows the yellow curve. Now let us try to verify the chain rule. That means we think about the derivatives of these three functions. First, we illustrate the derivative of the function f at a. We do this by drawing the slope triangle. By dividing the length of the vertical leg by the length of the horizontal leg, we get the slope of f at a, that is, the derivative of f at a, which in this case is negative 1.4. Next, we want to calculate the derivative of g at the position f of a. Again, we do this by drawing the slope triangle. And again, the derivative of g at f of a is given by the slope of this tangent, that means by the quotient of this length of the vertical leg by the length of this horizontal leg. And in this case, this derivative is 0.61. Third, we want to calculate the derivative of capital F at the position a. Again, we draw the slope triangle. And we receive a slope of negative 0.86. Now you see that I have written the formula for the chain rule here. The derivative of capital F is given by the derivative of f at x, which is in this case negative 1.4, times the derivative of g evaluated at the point f of x, which is 0.61 here. The product of these two values is negative 0.86. Now we can verify the chain rule for this point A by verifying that these values here fit to what we see at the three slope triangles. The slope of negative 1.4 fits to this tangent, the slope of 0.61 fits to this tangent, and the slope of negative 0.86, which is the product of those two, fits with what we see at this tangent here. So in very short terms, what the chain rule basically says is that this slope is given by the product of that slope and that slope. And if we think of derivatives as rates of change, we have this rate of change times this rate of change gives the rate of change of the composite function of these two. And suddenly the chain rule becomes rather simple. Again, we have only verified the chain rule for one point A. By animating the position of A and by taking protocol of these derivatives up here and by verifying that they fit to the slopes we see in these slope triangles here, we can at least roughly verify the chain rule for that complete example. So let's do the animation. I encourage you to stop the video at any point during the animation in order to verify that the slope triangles, the tangents, and the numeric values for the derivatives fit together. Now let's consider some specific examples and calculate the derivatives of composite functions by means of the chain rule. As a first example, we consider the function capital F of x equals x to the power of 5 plus 3x to the power of 2 plus 4 to the power of 100. The first step is to realize that this function is a composed function, and the second step is to identify the two functions f and g. We generally call g the outer function and f the inner function. In this case, it is easy to see that f, the inner function, is the expression in the brackets, and that g, the outer function, takes it to the power of 100. We can therefore write: for both the inner and the outer function, we now determine the respective derivatives. So the derivative of f prime of x, is 5 times x to the power of 4 plus 6x, and the derivative of g prime of y, is 100 times y to the power of 99. Note that we use y as the variable for the outer function g in order to distinguish it from the variable x, which is used for the inner function. We can now build everything together using the chain rule. So we have capital F prime of x equals, now the first term is g prime evaluated at f of x. So this is 100 times something to the power of 99, where we replace this something by f of x. So we get this. And this expression has to be multiplied by f prime of x. So we have times 5 times x to the power of 4 plus 6x. This is the derivative function of capital F. Let's have a look at another example. We look at the function f of x equals square root of x to the power of 8 plus 4x squared plus 8x. First, we know that in this example we have chosen small f as the symbol for the function we want to differentiate. So because small f has already been taken now, we can't use g and small f as the name of the inner and the outer function. As small f is a very typical name for a function, we run into this situation very often. So this is why we usually use u and v as names for the inner and the outer function. Again, in this case, it is very easy to see that the function f is a composite function. And it's also easy to see that the inner function is the expression under the root, and that the outer function is the root itself. Again, we start by calculating the derivatives of u and v, which is for u prime of x equals 8 times x to the power of 7 plus 8 times x plus 8. In order to calculate the derivative of v, we first realize that to take the square root of something is the same as to take this something to the power of 1/2. Because now we can apply the power rule for differentiation, which means taking down the exponent in front of the expression and reducing the exponent by 1. This also works for fractional powers. So we have v prime of y equals, now I put the 1/2 in front of the expression and I diminish the exponent by 1. So 1/2 minus 1 is minus 1/2. And we can simplify this expression further by applying the rule that whenever we have a negative sign in the exponent, we may take the inverse value of this expression and leave away the negative sign. So that gives 1/2, and now the inverse value, which is 1 over y, and now to the power of 1/2 without a negative sign. And I personally prefer not to have fractional exponents. This is why we replace it by the square root again, which gives us this expression. Now we can build everything together using the chain rule. We have f prime of x equals... Now, because we're using u and v instead of g and f, let's just rewrite the chain rule using u and v. That means we start with v prime, in which we plug in u of x, such that we get 1 divided by 2 square root of x to the power of 8 plus 4x squared plus 8x times u prime of x, which is times 8x to the power of 7 plus 8x plus 8. Although this is a perfect formula for the derivative of f, we're always happy to simplify the final result as much as possible. In this case, two things suggest themselves. First, putting this expression into the numerator, which gives this. And second, reducing the fraction by 2, because the factor 2 appears both in the numerator and the denominator. Of course, we have to reduce each summoned in the numerator, which is no problem, because there are 3/8. So the 3/8 turns into 4s, respectively, and the 2 in the denominator turns into a 1, leading to this expression. I want to finish this video with the last example, which is an application of the chain rule in order to prove the quotient rule. Remember that the quotient rule is the following. If I have a function capital F of x, which is defined as the quotient of two functions f of x divided by g of x, then we know that the derivative of capital of x equals f prime of x times g of x minus f of x times g prime of x divided by g of x squared. That is the quotient rule. I now want to use the chain rule along with the product rule in order to prove the quotient rule. Remember that the product rule is the following, that if we have capital F of x equals fx times g of x, that then the derivative of capital X equals f prime of x times g of x plus f of x times g prime of x. That is the product rule. To prove the quotient rule, we write capital of X, which is f of x over g of x. And now we can write this as f of x times g to the power of minus 1 of x. And we call this function g to the power of minus 1 of x by a new name, which is, for instance, h of x. So then we have f of x times h of x. And now you see that is something where we can apply the product rule to. We will do this later. But first I want to calculate the derivative of h of x. And that is what we use the chain rule for, because h of x can be seen as a composite function, v of g of x, where v is nothing else than the inverse function, taking the inverse of y. The derivative of v is v prime of y equals, and now we apply the power rule, which also applies to negative exponents. So we have to take the negative exponent of negative 1 before the expression And then we have to decrease the exponent, which is -1, by 1. So we get -2, which also is minus 1 over y squared. Using this derivative of v, we now can write down the derivative of h using the chain rule. Applying the chain rule means we have to start with the derivative of the outer function. The outer function is v. The derivative is -1 over, well, y squared. But we don't use y squared, we plug in for y g, which is the inner function. So we have g of x squared down in the denominator, times the derivative of the inner function. The inner function is g. We just write g prime of x. Can simplify this a little, writing -g prime of x over g of x squared. Now we can finally apply the product rule for capital F of x. So capital prime of x is, applying the product rule, f prime of x, now times h of x, plus f of x times h prime of x. That equals, well, h of x is actually 1 over g of x. So this expression simplifies to f prime of x over g of x. Plus, and now this expression can be rewritten using our expression of h prime of x, which gives f of x times -g prime of x over g of x squared. Now this is the common denominator, g of x squared. So if we expand the first fraction by g of x, we can take everything to the common denominator. And we get, well, f dash of x. Now we have an extra g of x because we expanded the first fraction by another g of x, minus f of x times g prime of x. And now we divide everything by the common denominator, g of x squared. And now we are running out of space. But this doesn't matter because we're finished. This is the quotient rule. So admittedly, that last example was a bit quick, but I just wanted to demonstrate to you, apart from the more detailed examples before, how the chain rule can be applied in proofs, that means in more abstract mathematics. So that's it for this video. Thanks for watching and see you next time.